Adeline Paiement, removing cloud shadows from ground-based solar imagery. Let's stick to 5 to 5 formula.
So to give you a little bit of context first, initially we were not interested in clouds. We were interested in studying the behavior of filaments and active regions in ground-based images. Unfortunately, we quickly realized that all the automatic detection algorithms are really hindered by clouds in these observations. So we asked, well, our master student, Amal, to have a look at this problem, and she worked with Jay, who's a postdoc on the project, sitting just at the back of the room. And so we wanted to recover the active regions and the filaments that are still visible behind the clouds. So we're only dealing with semi-transparent clouds. And the main goal of this side project was to remove as much as possible these clouds so that the detection algorithms could work more properly on these filaments and active regions. In order to do that, we trained a UNet model, which by now you all are familiar with, and we asked this UNet model to predict a mask of cloud contamination so that we could remove this contamination from the images by simply adding in the intensity that was removed by the cloud. And then after cleaning the images, we can verify that the detections algorithm now succeed in finding the active regions and filaments. We have experimented with two ways of training this neural network, a classical fully supervised way and a conditional GAN setup where a small discriminator scans small patches, local patches of the image that is produced by our neural net, by our UNet, and compares with the original cloudy image and determines if this image is actually a real one or one that was produced by the UNet. The aim being that the UNet becomes so good at predicting very realistic images that it can trick the discriminator into believing these are real images. In order to train these networks in both setups, we need pairs of clean images and cloudy images. And by nature in this problem, we don't have the clean counterpart of cloudy images. So we went on to designing some new data sets based on clean images, on top of which we added some artificially generated clouds. Then we could train on this artificial cloud data set and test on real clouds. So here are some first results on both H-alpha and calcium-2 images. The first row for each case is synthetic clouds and the second real clouds. Here we have been training on clouds that look very fluffy, and for these initial data sets, many clouds have this strict texture because these images are from Paris Meudon Observatory, where the image is scanned by a moving slit, which makes the cloud appear like a vertical line or diagonal line. So even though the texture of the cloud is different, we are still find that our two neural networks are fairly good at removing the clouds. And we also found that the active regions of filaments are generally pretty well restored by the cleaning, as demonstrated by the results of the detection algorithms, which are quite improved compared to the initial cloudy image case. This is still being evaluated with now more data. We are building a second data set with images from other observatories, BBSO and Kanzerhofer, and also more different cloud textures. We're going to also include these strict detector in our new data set. So if you would like to play with the initial data set, it's already online, and we're aiming to publish the new one fairly soon. And the cloud removal code, well, neural network is also published here. Thank you.
Also, thank you for this interesting poster. And do we have questions from the auditorium? Yes, please.
Thank you for this interesting talk. So I have maybe two questions. So the first one is, if you go back to the method overview, maybe. So what are you actually using for a target here for training the architecture?
We're using the synthetic data set we generated. So we have some clean images to which we add artificial cloud texture.
But you're performing this like separate from each other. It's not like an end-to-end training that you're using for this. So you're first generating samples of like clear observations and cloudy images, and then you're training separately afterwards.
The clear observations are real ones.
Yeah.
We don't generate them. We just pick
right. But
them.
you create the synthetic pairs for those.
We added the synthetic clouds on top of it. It's just a random combination of different deformations of a basic cloud texture. It's not something that we generated using learning.
I see, okay. And maybe what I noticed in this image here at the top for the architecture is kind of that the image on the right, you can see like way more active regions, especially on the bottom left. Is this something that can happen, that there are synthetically active regions introduced by this subtraction?
Well, we're still in the process of investigating this, but there may be also a contrast issue here. It's difficult to see the active regions here, but if you zoom in, you can, like the bottom active regions here, you can actually find it if you zoom in and stretch the contrast locally. So it is actually here. We're not inventing it. Of course, we're going to verify that on a larger scale. The detection of structures that we're currently doing is going to be compared against detections from neighboring times and possibly also other observatories at similar time to validate that the features actually exist, that we are not creating them.
Sounds good. Thank you.
Do we have more questions? So when you have online questions, I might ask one question myself. Could you please tell a little bit more on this artificial clouds training data set generation? So is it just kind of plain black masks, or you somehow can play with transparency and the thing that they are not uniform? Because, you know, if it's kind of, okay, very big and dark cloud, it's well, okay, it's basically those pixels are not present. And if it's somewhat transparent, then it's the question of the contrast rather than intensity. So.
Yes, there is transparency. In fact, we have been varying the level of transparency, and we are in the process of analyzing the results as a function of the strength of the cloud coverage. So we are now looking at whether the method has different performances when the clouds are thin or medium or very thick. So we have been varying the transparency in order to investigate this as well. But for one given image, there is also a variability in transparency across the solar disk.
You mean variability across the mask? So the masks, they are not uniform in size, so to say. Okay, I got it. Thank you. So since we don't have questions, thank you. Thank you so much. And